we're quite used to the idea that a North Pole brought close to another North Pole will create a force of repulsion. That the interaction of the magnetic field around this magnet with the magnetic field around that magnet will give rise to a force that pushes the two magnets apart. But what if we replaced one of these magnets with an electromagnet? So here I have a coil of wire which is simply an electromagnet. And if I turn this on, is it all switched on? Let's see what happens. So let's see what happens. Here I've formed a North Pole. Oh, it was tiny. Oh, look at that. I'm pushing the magnet with the magnetic field generated from this electromagnet. I can create motion by passing an electrical current through these wires. Now this idea is called the motor effect, and I've got lots of demonstrations here to show it in action. So this is quite a fun experiment. It's called a sliding wire. What I've got is two parallel metal poles and a flexible movable just piece of metal that's going to just sit on top. And this time, rather than have an electromagnet pushing a fixed magnet, my fixed magnet is so big and heavy that it's actually just going to push the wire that is in the circuit because it's able to do so. So when I press this button, we should see a force exerted on that wire, making it move. How good was that? We can predict the amount of force acting on that wire. It's only dependent on a small number of things, and here they are. The first thing that it is dependent upon is the magnetic field strength of the permanent magnet. If I put a much stronger magnet there, then it's going to apply far more force in that scenario, and the wire's going to fly off. So how strong that magnet is, the magnetic field strength, is a really important part of this. If I put more current through that wire, I find that there is a greater magnetic field created around the wire. Remember we said with electromagnetism that more current made a stronger electromagnet? Well, having more current in that wire there means there's more of a magnetic field being generated around the wire to interact with the permanent magnet. And of course, the length of the wire explains just how much of the wire is generating magnetic field. More wire means more electromagnetism. So these three things sit together in this formula. Now some of the quantities here have symbols that might not look very familiar, but let me take you through. The simple equation for this is that force is equal to magnetic field strength. Well, here we give it the symbol capital B. Current is measured or represented by the symbol I, and length of wire, lowercase l. And just to be clear, the units of these, we have newtons. The magnetic field strength is actually measured in a new unit for us. It's measured in Teslas, after Nikola Tesla. Current is measured in amps, and length is measured in meters. We could, in fact, define the magnetic field strength of a fixed magnet by taking the force per unit current length of an electromagnet that it is pushing against. And this is actually how we define the magnetic field strength of a permanent magnet. We look at its effect on an electromagnet whose other quantities we know. We can experiment with some things here. What happens if I change the direction of the current by swapping these two over? Do you want to make a prediction as to what you think is going to happen? It went the other way. So the direction of the current is really important here. To remind, this is what it normally does. It goes that way. What would happen if I changed the direction of the magnetic field? So, take this out, turn it that way round, and put it back in like that. Do you want to make a prediction about which way it's going to go? Oh look! Having the magnetic field the other way round made the force acting on it act in the opposite direction. Now, a scientist called Ambrose Fleming came up with a way of remembering which way the force is going to act on a movable wire like that, based on the direction of the current and the direction of the magnetic field. It's called Fleming's left-hand rule. So here is my left hand, and I've put my thumb, first finger and second finger, at right angles to each other. They're all in like X, Y, and Z, you could almost imagine. Now these three fingers are going to tell us the direction that the force is going to act in relative to the current and the magnetic field. So first of all, my thumb represents the direction of the force. In the sliding wire, that was, is it going to push it to the right or to the left? Here, it's the thumb that represents the force. But then the first finger represents the direction of the magnetic field. B. And the second finger represents the direction of the conventional current I. So I'm going to write an F, B, I, as in the FBI. But the FBI shows me the direction that the force will act in if I know the magnetic field direction and the direction of current. These are useful, but don't write these on your fingers in the exam. You need to remember FBI. So does FBI work with this apparatus? First of all, let's figure out which direction current is flowing. Conventional current, if you remember, was the flow of positive particles towards the negative terminal. So the current is flowing down this red wire, through towards you, and then back up the black wire. So current has got to be towards you. This magnet has got north written here and south written down there. Now that means that the magnetic field pointing towards the south, like a compass, is going to be down, which means the prediction is that the wire should feel a force pushing it to your right. Fabulous. Now that we're happy that electrifying an electromagnet near a permanent magnet will cause motion to occur between the two, we can have a look at some of the applications of this technology. In the uses of electromagnet, we looked at a speaker, and what is going on here is just that the current is just varying with time, creating an off-on pushing of one magnet against the electromagnet, causing the speaker cone to move up and down. By changing the frequency that the current is varying, I can change the frequency of the speaker cone, and this will produce all of the sounds that I'm used to hearing. We don't need to have a speaker cone to make the same sorts of noises. Here we just have a thin strip of aluminium which is going to carry a current going through this strong magnetic magnetic field. The alternating current that is coming from this signal generator is going to pass through the aluminium. When the current is flowing one way, the aluminium is going to be pushed one way by that magnetic field, and when the current goes the other way, then the aluminium is going to be pushed back again, and this continual up and down motion sets off the vibration that we hear as sound waves. Here it's inaudible. As I turn it up, that is sound just coming from a strip of aluminium.